Okay, so this is 10.1a for your next exam, which is on Friday. So it's using the Runge-Kutta method to approximate solutions to ODEs. So the first thing we want to do is assign our variables in this chart here. So we need our h is going to be equal to 0.1 because that's what we're evaluating the function at. Our y sub 0 is going to be equal to 1 because we're told that. Our t sub 0 is going to be equal to 0 because we want it to be, and so we set it to that. And then our function of t and y is going to be t plus y because that is the function that we're given to evaluate. Okay, and now we're going to use this chart over here to solve this ODE. So I'm actually going to start with these little guys over here. So for our K1, we have F T sub naught, comma Y sub naught. These are zeros. Okay, so evaluating this function at T sub naught and Y sub naught, we get 0 for our T sub naught because that's what we set it equal to here. And then we still have our Y sub naught here equal to 1. So we have K1 equals 1. And for K2, we're going to use the formula given here. So we have our F equals T naught plus 1/2 H, comma, Y naught plus 1/2 H, and then times our K. So for this one, we're going to get F evaluated at 0 plus 0.15 because that's 1/2 of our 0.01 or 0.1, and then comma we have our 1/2 times 0.1 and then times our 1. So for this first one, oh I'm sorry, plus 1 here. So for this first one, you're evaluating the function at 0.5 and then 1.05 for your t and your y. So you have your t 0.5 and then plus your y 1.05 gives you 1.1, and that's your K2. So for K3, we're going to use this formula over here, and we get our function evaluated at t sub naught plus 1/2 h for the t, and then for our y, we have our y sub naught plus 1/2 hk2. Okay, so very similarly, we're just going to plug in those values. So our function evaluated at 0 plus 0.05, and again, I'm sorry, this is a 0.05 because it's half of our 0.1 up here. Sorry, so we have here, we got a 0 plus 0.05, 0.05. And then we have 1 plus 1/2 times our 0.1 times our K2, which is 1.1, because we determined that up here. So when you plug in all those numbers, you should get your function evaluated at 0.05, and then 1.055. So we have 0.05 plus 1.055, and you should get 1.105 for your K3. Okay, and now for our K4, I'm going to make our screen smaller so we can fit it all in. Okay, so for K4, we get our function evaluated at t naught plus h comma, y naught plus h times k3. Okay, so it should look something like this. Your function will evaluate at 0 for our t naught, and then 0 plus 1 for our h, comma, we have our y naught is still 1, and then plus 0.01 times our k3, which was 1.1005. Okay, and so you should have your k4 equaling your function evaluated at 0.1 and then 1.1105 for your y value. When you plug that in, you get 0.1 plus 1.1105. You should get 1.2105. Okay, so now we can use all of these coefficients here to solve for our value. So we have y evaluated at 0.1 is approximately equal to 1 plus 0.1 over 6 times our k1, times our k1, which we determined to be 1. Our k1 determined to be 1, and then plus 2 times our k2, which is 1.1, and plus 2 times our k3, which is 1.105, and then plus our k4, which we got 1.2105. Okay, and when you plug all that in, you should get something that looks like this. 1.1103416667. I know it seems silly to carry all those decimals, but I would say that it is kind of important for this type of problem, being that we're really concerned with the decimals here. So try to carry as many as you can, and definitely save them in your calculator as well. So that's actually the answer for the first part of your test. And the only thing that's left is part B, which is calculating the error. So it's given to you here that this is the analytical solution. So Dr. Norton gives you the analytical solution. Y equals 2e to the t minus 1. And all you're going to do with that is you're going to plug in this value. So you're going to evaluate it here. So 2e.01 minus 0.1 minus 1. And you should get for this one, this is the exact value, by the way. Well, I guess it's technically not, so let's still do that because we're assuming that our calculators are rounding. Your calculator display only shows 9 digits, and I'm assuming that this number does not precisely end at 9 digits, but I don't think he'll be too picky on this part since it is technically like the analytical solution. This part over here is definitely needs a tilde because the Runge-Kutta method can only approximate. It's not even trying to be a direct equality. So anyway, so when you do that, you should get 1.1103411836, and all you're going to do from here to find the error is you're going to take the absolute value and you're going to subtract these two numbers. So we have 1.1103411836, and then minus our 1.1103416667 absolute value, and you should get 1.69 times 10 to the negative 7th for your error here. So hopefully that made sense. Please let me know if you have any questions whatsoever. Like I said on last video, please just be super careful with your decimals. It's super easy to mess up somewhere little, and it'll definitely show up later on in the problem. Since you have to plug in all these k values into the next k value, it'll carry through the whole problem. So if you have time, I do suggest doing it more than once on your test, just to make sure you didn't make a stupid error and then the whole thing's wrong. So let me know if you have any questions at all. Yeah.